your notes for this? Do you have your notes for this?
Any of my notes?
Yeah.
No, I gave them to you on your desk.
Okay, team, I'm going to get started. Thank you for coming. It's really interesting because I thought I'd be talking to like 4 kids that were going, hey, I'm not quite sure, I just want to brush up. I'm presuming that if you're here, you've had a decent crack at the flex work and you're either wanting a little bit of help with it, or perhaps you just are itchy and want to make sure you don't miss a damn thing just in case you can glean anything extra and give it your best shot next week. So happy to approach it from any of those levels, entirely up to you. Can I just remind you about what to bring next week? Because the weird thing is I'm asking for you to have coloured pencils or highlighters or both. That's really unusual for us. We're not geography students. But, sorry, I keep trying to use that line. I get a couple of giggles. But anyway, it's something that would be useful. And hopefully when you did the flex work, you saw why I got you to use them. So you can highlight either in the table or perhaps you can use it to highlight which ones are the recombinant types and so on. So that's a good thing. I'm going to start with the definitions. I'm going to race through this as fast as we possibly can. How do you want to approach this? Do you want me to just tell you what the definitions are? Do you want me to check in with you? Do you want me to presume you know them? Yeah, you're right, yeah. Okay. Chromosome maps are intended to show you what the relative position of genes on a chromosome are. When I say the relative position, I mean relative, not absolute. Physics students understand the difference between these terms really clearly. Absolute means it's exact, it's precise, this is exactly where it is. Relative means that where is A compared with B and compared with C. So it's giving you their rough position on a chromosome. So firstly, this is making a presumption that these genes are on the same chromosome, and we have to know that they are, and there's information that we can get by looking at rates of recombination that tells us whether they're not. So in a nutshell, a chromosome map is just a map which signifies the relative positions of each gene on a chromosome. The crossover value, which we also call COV or recombination frequency, RF, is simply looking at how often recombination occurs, in other words, crossing over during meiosis occurs, for a given pair of genes. If we're considering gene A and gene B, then what we want to do is look at how often would those gene loci cross over independently of each other, such that if you've got a heterozygous individual, gene A will go from one chromosome and flip over to its homologous partner. So, in other words, getting the little a with the big B now instead. Is everyone okay with that without a diagram? All right, because I'll do some diagrams for these later on. A linked gene versus a synthetic gene. I actually like to start this with a synthetic gene definition. Things that are synthetic, genes that are synthetic, are on the same chromosome. Genes that are linked are genes that are close together on the same chromosome. If genes are linked, they are always synthetic. But if, for example, you in this second row here, where there's a whole bunch of you, if you all represented a gene each, the first gene is linked to the second gene, which is linked to the third gene. But while each one is linked to the one that precedes it and follows it, the one at the end is not linked to the one at the start, because there are so many opportunities for crossing over to occur. The rates of recombination there would be equal to 50%. What's chiasma? Chiasmata. All these things just mean crossing over. Chiasma is the crossing over point. You have an optic chiasma in your brain which takes the optic nerves from each of your eyes, it crosses them over so that your left eyeball goes to the right side of the optic region of your brain, and vice versa. That's crossing over. I'm going to backtrack for a second. You've got a question?
For the linked gene,
Yep.
I remember you saying in class that they're linked if they cross over separately less than
Quite right. So linked genes will have a crossover value of less than 50%. Genes that are not linked will be 50%. What does that mean? It means they're inherited independently of each other. We'll look at that in a little form in just a second. Everyone okay with crossing over?
Yeah, sorry. With chiasma,
Yes.
is it the actual point of crossing over or is it the act of crossing over?
Crossing over is the action. Chiasma is the location. Chiasmata is the action, just like crossing over. The test won't be a definitions test. It will be an application of what you know, which is probably a little bit more perilous because it means you've got to know the definitions before you can apply them and, analyse that data. Question 5, how's the frequency of crossing over influenced by the location of a pair of genes? This is very simply that the further away you are, the more frequently you cross over. And converse. The closer you are, the less frequently you cross over. Question 6, why do Mendel's laws, segregation, assortment only apply when genes are not linked? Mendel did his work as factors of inheritance that were all independent. He thought they were all tiny little units that were just like beads. And if you were heterozygous or something, you had two slightly different beads, completely independent. And you could shuffle them up in any order. And his first law, this question's a little bit misleading, his first law always applies unless something's going to go wrong. Segregation will always apply. The factors of inheritance will go into separate gametes from each other. You can't have any two of the same alleles in the gamete together. That's his first law. The second law, the law of assortment, only applies when things are either independent on separate chromosomes or if they behave as though they're independent. Behaving as though they're independent is crossing over. If they behave as though they're dependent, they're linked, they stick together, they like to stay together. Any questions for me at that? Sweet. Okay, so here we get to the nitty-gritties. I can never extol the virtues of a key enough. Okay, so I've provided you with one as an exemplar of a key. All right, where you separate the phenotype from the genotype and you use letters that are nice and simple, not like our activity manual that complicates everything by putting, EB for ebony, and you just needed the E, you didn't need the B as well. Okay, so keep it simple and then refer to it whenever you're using things. This one tells you quite specifically that being small and terrific and ubiquitous are the dominant traits. Finally we get it, right. Being big and ordinary and confined, they're all recessive traits. What we call these things is inconsequential. It's the nature of inheritance that counts. Okay. Does everyone recognise when we look at this to start with that the first thing we're dealing with is a simple cross, even though we're looking at realistically a trihybrid cross? Yuck. We're only going to end up with a very small sample of stuff here. Let's just see how we go. All right. I'm not sure I'm under control. Just give us a second. All right, for this one here, which is not even working for me, even though I tried all this earlier for you. 1 second. Momentary pause. Really? There are days when technology won't cooperate with me. I was going to be able to write all over this for you and now I can't. 1 second, talk amongst yourselves. I don't want to type. Okay, let's try again. So, everyone good with that? And therefore, everyone's also good with this. Notice I put the little lines above. Please observe that convention when you are writing in your prac. If something could be misconstrued as a lowercase versus an uppercase, don't make us guess. Because when I look at the front, you know, and I see that's riches, I'm going to go, oh, I'm going to mark it wrong because it's riches, right? Don't make us guess. Make sure it's for certain. Right. So firstly, this is the critical part of your understanding. It pops up over and over again. If this particular parent here is homozygous dominant for both traits, remembering they got those from their parents, this person here is in fact, oh, not working again. Really? Sometimes. Right, good. This particular parent here had the arrangement on the chromosome of capital S followed by capital S, capital T, right, they were like that, which means that no matter how much crossing over happened, I should draw these as double-stranded chromosomes, but if these swap over, we get no new combinations, right? So this gamete that it's produced is in that combination. And when we produce the F1, you're all recognising, of course, that we're just looking at, half written here, but the heterozygous individuals for both. Good. Hieroglyphics, you like them? I like it. Should have been Egyptian. This is going pear-shaped. But you can recognise that this individual as an F1 would have all of the phenotype of the dominant characteristics for each of the three. We good? Heterozygous, heterozygous, heterozygous if you missed it. Okay. Can everyone see that this parent here is only contributing those three alleles on one chromosome? Yes? And this parent here is contributing these three alleles on the other chromosome. What that means is this offspring, the heterozygous, heterozygous, heterozygous person, is a consequence of being, you know, all right, good, excellent. So I'm going to play over here with my mouse, and instead I'll just draw them for you. You know, you've got this one here and this one here. This is all the capitals here. I can't do it with my mouse, but you get it, right? I look really so wrong. You laugh all you like. This is a little s and little t. Oh, look, it's saying it's back with us now. And these are little ones. This is important to remember. This is the offspring. All capitals and all lowercase, because this has a bearing on what happens for the next generation, okay, whether crossing over does or doesn't occur. Oh, all right. So I've answered that next question. You all good? Why doesn't it matter if crossing over happened? Because if it's big S crossing over with big S, no new combinations are ever formed. Well, it'd be small. Yes, quite right. Because that's the phenotype, not the genotype. The genotype was written in the F1 layer before. All right, if any one of the F1 is crossed back to the recessive parent, I tell you not to think about it. This happens in genetics all the time, that we cross things back to a recessive parent or a particular parent because they're of a known genotype. That's why we do it. So in this instance, we go the heterozygous, 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 mates with the homozygous recessive individual. Bear with me while this thing keeps flicking around, and I'll give it one last shot and then I'll retire it if it doesn't want to work with me. Reality for this stuff is that now this parent here is the one that could have how many different possible combinations if crossing over did occur? 2 to 3, 8 possibilities. I like the maths of it there, we're getting it, okay? So if crossing over does not occur, can you all identify that the gametes that you'll get will just merely be the separation of the 2 homologous chromosomes and then duplicate them, but just the separation of the 2 homologous chromosomes into their gametes? What does that mean? The big S, big T, big U, or the little s, little t, little u. Do we recognise that? Okay. So this one's reasonably straightforward, just to put those groups together. We're going to try. So we're going to get the big S, big T, big U, or the little one. And this parent here will only give us those. Good? F2 therefore becomes either this one here with this equals heterozygous, heterozygous, heterozygous. Yes? Phenotypically, do you recognise that they look exactly like their first parent? Good? If we put this gamete with this one, we go homozygous recessive for all three traits, and you'll also notice that they look therefore like the second parent. If no crossing over occurs, here's your big hint, the kids will look like one of their parents in entirety. Yes? They'll either look small, terrific, ubiquitous, or they will look big, ordinary, and confined. I was reaching when I was making this up for you. All right. So these are known as the non-recombinant types. These are the ones that occurred if no crossing over. Oh no. These ones that are happening if there's no crossing over occurring. Any questions? Right. Knowing that the arrangement of the alleles are either all of the dominant ones or all of the recessive ones, and not the others, is because we were told, presume no crossing over occurs. Now what we're looking for is those other 6 combinations that we just ignored, the recombinant ones. I'd love to be able to draw these up for you because this is kind of the fun bit. So I'm just going to do this separately for you where I know it might work, where I hope it might work. Sweet. When you've got your arrangement of your big S, tell me when it starts again. The big S, the big T, and the big U were on this one. And over here, on this other line that I haven't drawn yet for you, is the little s, the little t, and the little u, right? Now, again, I should draw them as double-stranded chromosomes, but I'm going to be lazy and not. Oh, this is so much slower than just scribbling it out. I had great hopes for today. All right. If crossing over is going to happen, then what's your result? Think about them. If crossing over happens between these first 2 spots, we just swap those over. So now I've got 2 more gametes to write down. Can you see them? Okay. If crossing over also happens, with these 2 spots, then I have also got those 2 combinations. So far, so good. If crossing over only happens for that second gene locus, I also have these 2 gametic combinations, which also leaves us with, finally, this combination. Oops, that's what we started with. Let's try again. All right. So you can find your 8 in total. Okay? Change each position one at a time. Don't repeat any. If I could draw it, you'd see it a lot faster. I can hear this thing fighting with itself trying to get. That includes the ones that were not crossing over, the big S, big T, big U.
And so we should not draw the non-recombinant.
Not for this. This one's asking you specifically what are the ones from recombination. So what you'll notice here is that when you then produce your F2, none of them will look like either of their parents entirely. They'll have bits of both. Yes? All kids will look different, and there will be 6 new phenotypes that have resulted. So I really don't mind which way you've accumulated your results for this one, because you might be looking back at what happens with the others. If you're looking purely at this, only the recombinant types, each of them is 1/6. For the percentage, you'll change that over, all right, and it'll be the equivalent of 1/6. So the main thing from this is the recognition of what constitutes a recombinant type. This is where it gets to the nitty-gritty, and it would be really useful for us to see how this part works. Sure you can. Yeah, look, whole numbers are really good for chromosome maps, because I keep reminding you all the time that chromosome maps are based on using population statistics. Population statistics are just that, they're fallible. They're just numbers that have been gathered from probability. And probability is completely fallible, okay? So just because, for example, you've got a gene recombination rate between A and B of 10, and B to C might be 5, A to C is not necessarily 15, it could be 13, or it could be 25-ish, right? So approximate numbers are good enough. Do round to the nearest whole percentage. Yep, yeah. That depends, and that's what I was saying. It depends on how you want to accumulate your results. If in this particular one you only used the 6 gametes that were the recombinant types, then there are only 6 phenotypes, so it'd be 1/6. If you also included these ones here, the non-recombinant types, then it's 1/8. No, look, we'll see it in the results that you've done. But strictly if you followed through what's presented by that cross, only the ones for crossing over, then they should only have 6 responses. Yep. That's fine. Why? Because map units are no longer percentages. We call them map units now. Okay? So that's irrelevant. Or centimorgans is the other name you could use for it if you wanted to. Now this part's the cool part. This is where you get cracking on it. When you look at this stuff here, were you to consider, for example, what stuff is going to be recombinant types? When I look at all these ones across there, that is a non-recombinant type. It's got all the dominant characteristics. Can you see those? And we would go through all these going, yeah, that's non-recombinant, my hand's not real steady. Now this next one here is a recombinant type. Can you see it? Because it's got that one, recessive, followed by dominant. Yes? Now, accumulating your results and being able to see what are recombinants is the important aspect. So we're going to review this chart again in just a moment in light of the question that we're given. So the question says, firstly, let's look only at genes S and T to determine their crossover value. So this one asks you, how many are small and terrific? You go back here and you only consider genes S and T. Small and terrific, 1, 2, 3, 4, 5, 6, 7, skip that one, right? 8, 9. 9 are small and terrific. Then you've gone through and you found out how many are small and ordinary. When I see small and ordinary, I recognise that straight away as a recombinant type. Because 1, the first trait, small is dominant, and 2, the second trait of ordinary is recessive. Dominant recessive equals recombination. Dominant or recessive are non-recombinants. We got it? Yes? All right. So I had 9 of the first. How many of the next one did we have? 3. How many of the next one did we have? Now, how many of the next one? 7. Okay. So we went 9, 3, 1, 7. If you took a highlighter and highlighted which ones were the recombinant types, it was this one here and this one here. Those 2 are your recombinant types. So that was 3 and 1. That's 4 out of how many in total? 4 out of 20, which equals 2%. So here in this, you're just literally following that. Sorry? 20%, sorry. 2%, 20%, all good. All right, so you write your 20% in here as a consequence of that. Total of your recombinants divided by the total number of individuals that were created, multiply it by 100. Round to the nearest whole percentage. Done. Dusted, right? Then you look at T and U. Everyone okay with working those numbers through? Right, let's just get some numbers from people. Can anyone tell me T and U? Next one? Yep. Okay. Two middle ones added up together, divided by all of them in total equals 30%. All right, so we've got a 20%, a 30%, keep remembering this for us, and then we've got the potential to do gene maps now. Okay, here we go. If we put the T here, oh goody. So if we put the T here, it doesn't really matter where you start, and the S here, I'm doing this quite obviously to be obtuse to what the results are that you've probably written down. You probably wrote exactly the reverse. If T to S was what, 20? Yes? And you also did T to U. What was T to U? If T to S is 20, T to U was what, 30? So could you recognise that we could write it here? Yes? That's one version of the map, and the other version of the map would be T to S being 20 and U being 30 over here. So there's my U, there's my T, and there's my S. Everyone sweet with that? Yeah. All right. So there are two versions of the map you can draw based on that information. Okay? Questions? Shoot.
Would it be okay, because obviously the TDU is the 30% difference, would it be okay to start with that instead of starting with the...
Absolutely. I often extol the virtues of starting with the biggest one first, but for this purpose it didn't really matter. We're just throwing them out there. Yep. Doesn't matter which one you lay down first because you're still going to get these two results. Okay. So you look at this and you say, well, I need to narrow it down. So obviously I need to know what? U to S. Okay, so that's what the whole map gets you to do next time. So now you do the U to S and you found out the values for those, you've added them up, you divided it out, and then you worked out that that was what? 10. So therefore you recognise that only one of your gene maps is correct. So therefore that becomes the gene map that you're going to work with at the end of the day. To summarise your results, you've placed them in this table now. So here your result summary was your S to T was 20, was it? Good, still not working. I hate you. Not nearly as much as you hate me, I'm sure. So here 20, S to U was what? 10, and T to U was 30. It's useful to put the rest of these in the locations. Do you have to? No, because they're just repetitious. You can leave them out if you want, or you could fill them in. It's inconsequential to us. It's important that you recognise that gene S and gene S don't cross over and gene T and T don't cross over and so on, because they are homologous partners. Okay? We're only talking about crossing over with respect to other gene loci. All right, so now that we've understood that, we recognise that we're only dealing with that gene map which shows the relative location where S and U are the furthest apart and T divides them. Okay? Did everyone get that chromosome map? All right, so our furthest distance here was in fact the 30. Pardon me? S divides them? Yes, okay, let's draw it up. So based on our knowledge, here's my pretty little line that I can't even draw. All right, so what was our furthest distance? It was 30. So you'd put your 30 here. What do we got? Who was 30? U and T. All right, so I'm going to flip this map from last time just for fun. S and T were how far? 20? So these guys here, oh, yep, close. Yeah. My prowess is really good. All right, and so you've got that. Now, What are some important aspects? You'll notice that on this chromosome map that I've given some relative locations. These are relative locations, not absolute locations. I've implied the map distance. Firstly, I've written it in here, but I've implied it in a kind of a scale that I've thrashed out there. Be very careful about the way a question's phrased. If it indicates that it wants a scale very specifically drawn, then do that. Okay? Any questions? You may have this map completely flipped. They're both identical chromosome maps.
I was just wondering, with mappiness, where would you use that? Because your rat percentage would really, really
When we say what is the crossover value, all right, we express that as a percentage. And then from there on in, when we put it on this, these are now map units apart. So it depends upon whether you're being asked a question to phrase a response for. You can either call them centimorgans or map units, but they're no longer percentages once you've gotten past what is the rate of recombination. All right, so now these, if you're describing the relationship here, you would say that U and S is 10 map units apart, not 10% apart. They're no longer percentages. We good? All right. So pretty much I think we're there. This last page just let you scribble any notes for those of you that are feeling really insecure and want to write some other bits and pieces down. The prac itself will just encompass carrying out these tasks and analysing what you produce. Any questions for me? Sarah? Okay. Chiasma is the physical location of the crossing over. So my example for that I gave you was a relative one that we've literally seen. When you dissect the brain, you see the optic chiasma. All right? So that's the physical point is chiasma. Chiasmata is the process of crossing over. So chiasmata and crossing over are literally interchangeable terms. So the process whereby the homologous chromosomes in prophase 1 of meiosis get next to each other. Whenever the corresponding gene loci are in contact, they can break and swap their information, and that is happening as a process known as crossing over or chiasmata. That will continue through metaphase 1 of meiosis, and it will terminate at anaphase 1 of meiosis when the homologous chromosomes are completely separated. All good? Multiple crossing overs can happen. So more than one gene loci can swap over. We good? All right. Have a great weekend. We'll see you next week.